Hello. And what's up? Today, we'll look at how WwiserR allows real-time procedural placement and modification of spatialized ambient sound beds, even at runtime. When I started working on this system about 2 weeks ago, I first defined a list of specifications that I wanted this system to implement. As such, I wanted the ambient beds to be properly spatialized and directional. For example, let's say we want an ambient bed to play for this forest. When the listener is inside the forest, it should be fully encompassed by the ambient bed, meaning that the bed should fully spread around the listener and tie to the world orientation. When the listener on the other hand is outside the forest, the ambient bed should spatialize accordingly, meaning it should become increasingly directional as the listener moves away from the forest, and spread the sound correctly to accurately represent the shape of the forest, while respecting the panning baked in the ambient bed audio file, as well as its world orientation. Next, the sound should properly propagate through AK rooms and portals. For example, if the listener is inside a building, the forest bed should correctly propagate through the building's doors and windows. Furthermore, the system should apply and propagate any late reverb set up on corresponding AK spatial volumes. All of this should work for any ambient bed audio file channel format, whether it's mono, stereo, quadraphonic, 5.1, ambisonics or any channel format supported by WwiserR. Before continuing with the integration requirements, let's see how all this works together in a short demo. To correctly play and spatialize the ambient beds, the system takes in localized weights for each bed. In this example, every tree in the forest has an associated weight representing the size of the tree. These weights can be adjusted at runtime. As such, the system can respond to, for example, chopping, planting, and growing trees. Similarly, weights could represent the depth at different positions inside a water or fluid volume, local rain intensities, and so on. At this point, weights are fed into the system via dedicated weight components. In the future, I'll add more ways to input weights without requiring such components. Finally, as always, I want the integration and authoring to be as simple yet flexible as possible. In this case, this includes keeping the number of required buses and RTPCs per bed to a minimum, to reduce the required integration time, as well as the risk of introducing bugs when scaling up or iterating on the game. Currently, the system can fully work with as little as 2 auxiliary buses and 2 RTPCs for an entire game. However, as we'll see later in this video, it's possible to use additional aux buses to freely organize the system within the Wwise mixing hierarchy. Now, let's look at how this system actually works and how easy and flexible it is to set it up. I'd like to invite you for a moment to think outside the box with me, as we're about to embark on a mind-boggling multidimensional metaphysical experience. When watching the demo earlier, you might have noticed some weird spheres hanging in the sky. Let's zoom in on those, as this is where the magic happens. What we're looking at here is the AK room component in which the bed is playing. To clarify, when multiple trees or weights generating the same ambient bed are spread across multiple AK rooms, a single instance of the bed is automatically created by the system for and tied to each respective room. This ensures that the beds will always properly position and propagate. In the same location sits a listener component as long as at least one bed is playing in this specific room. On the other hand, a radial AK sound emitter is spawned for each instance of each ambient bed playing in this room. You might have noticed that indeed 2 instances of the same bed were playing in the same room in the demo, and we'll get to that later in this video. Now, the spatial relationship between those 3 components is responsible for correctly positioning the ambient bed in the audio mix. As such, the position of the bed emitter relative to the room listener and room component is constantly set to the weighted average position of all the weights within the detection range, which I'll discuss in a minute, relative to the spatial audio listener, and scaled by this detection range. This means that when the spatial listener is inside the forest area, the bed emitter will be in pretty much the same location as the room and listener components. As the spatial listener moves further away from the forest area, the distance between the bed emitter and the room listener increases, while the angle between them and the bounds of the radial emitter, and as such, the perceived width or spread, decreases. To facilitate visual debugging, a representation of this relationship is shown in the top right of the screen, where the 3D crosshair represents the room listener, and the colored spheres the inner and outer radius of the radial ambient bed emitter. As the final part of the puzzle, the audio playing on the ambient bed emitter is routed to the room listener when the spatial listener is in the same room as the ambient bed, and to the room component when they are in different rooms. Lastly, if all of this still makes sense to you, you probably have already realized that the room listener also has to follow the spatial audio listener's rotation to make all of this work as intended. With all of this being clear, let's once again run the system and observe in the Wwise Voice Inspector that indeed the routing is working correctly, including both the interior and exterior late reverb associated with the respective AK spatial volumes. On the authoring and integration side, the project settings now have a default ambient bed auxiliary bus. This bus is purely intended to route the audio from the bed emitter to the room listener, and allow to route the sound anywhere you want in the Wwise master mixer hierarchy. As such, it does not handle any spatialization. It can however be used to tweak levels, filtering, apply effects and even downmix into a specific channel format if desirable. The ambient beds themselves are configured in data assets. Here we can assign the ambient bed Wwise audio event, as well as a distance and weight RTPC. These are both normalized to a range from 0 to 100. The distance RTPC sends the average weighted distance divided by the distance range, which I'll cover in a second. The weight RTPC sends the accumulated weight divided by a maximum value, which we can also set up here. Next we can assign a propagation auxiliary bus. This bus is responsible for the distance attenuation applied from a portal to the spatial audio listener, or between audio portals, when the spatial listener is in a different room than the ambient bed. Again, it's possible to use a single bus for the entire project, or as many different buses as you want, to define different attenuation sets, or organize your master mixer hierarchy. The default pass-through aux bus can also be overridden here, to allow further customization of the master mixer hierarchy. The distance range defines the range in within the system will look for ambient weights, and just as with the static sound emitters, we can pick any position between the spatial listener and its distance probe as the reference to calculate the ambient bed positioning. When it comes to spatialization, we can set a world rotation for the ambient bed. As an illustration, let's use a hard-pan quadraphonic file. When I'm in the forest, looking at the interior audio room, we can hear that the oboe and double bass are playing from the left, while the sax and flute are playing from the right. When I rotate the ambient bed by 180 degrees over the z-axis, the sax and flute are now playing from the left, while the oboe and double bass are playing from the right indeed. Finally, we can tweak the radius of the ambient bed emitter, and its relative inner radius, and set the crossfade time to apply when sending the bed to either the room listener or room component, when the spatial listener is entering or leaving the room in which the bed is playing. On the Wwise side, we can further tweak the spread over distance, using the distance attenuation on the ambient bed sound effect. The distance attenuation itself, however, is set up using the custom distance RTPC. So all that's left to do is add an ambient weight component to the tree blueprint, assign the ambient bed data asset, and the tree's weight, which we can also do at runtime using the set weight node. As mentioned earlier, if I want to create multiple separate instances of the same bed within the same room, I can easily do so by overriding the ambient bed group ID on the ambient weight component. Before rounding up this video, a quick peek at Unreal Insights shows that, in the current configuration, the CPU load sits between 200 and 500-ish microseconds per frame. As this is the first iteration of the system, there's certainly still room for optimization. Yet, I'd say these values are already very acceptable for a global system like this. And that's all for today. I am once again hoping that you liked this video and got a bit wiser in the process. Thank you very much for watching.